Hi all, welcome back to Cracking the Fang interviews. Today I'm going to be talking about this popular problem called subset sums. And this is an increasingly popular problem at Apple, Google, Amazon, and Netflix. One thing I'd like to note is this exact problem is not on lead code. So I've put a link from Geeks for Geeks, and I think it is a fundamental problem to understand concepts like recursion and subset related problems. So whenever you hear the word subset, you could sort of use this problem as your template to solve a question. And before I get into the problem, I want to quickly explain what a subset means. So if I give you a number, an array of numbers 1, 2, 3, 4, a subset of this array could be something like 1 or even 1, 2, which is also a subarray because it's consecutive. But a subset could also be non-contiguous elements like 1, 3. The only condition you have to follow is the elements that you derive from the original array have to be in order. So essentially, you can only have 1 and 3 and not 3 and 1. So in simple words, if you make parts of this given array, but as long as they are in order, they could be consecutive, they can be non-consecutive. As long as they are in order, it's a subset. Awesome. So now let's dive deep and look at the problem. It's called the subset sum problem. I'll have the link to the problem in the description down below. And what the problem says is you're given a non-negative set of integers and a value sum. You need to find out if there is a subset of the given set with sum equal to sum. So let's look at an example. If you're given this array of 3, 34, 4, 12, 5, 2, and you're given this sum 9, you need to create a subset out of this this array which sums to 9. So in this case 4 and 5 sum to 9. And on the other hand, if I give you the exact same array and I give you a sum of 30, there's no way to create a subset which sums to 30. Even if you take 34, 3, it goes above 30. 12 and 5 is 17, plus 2 is 19. There's no way to get to 30. So there's no subset that exists. So the concept here is essentially going to be, if you're given an array, for example 2, 4, 6 and 10 and a sum of 6, the subsets you can create is 2, 4 and 6. Both of these subset 1 and 2 sum to 6. So I think the idea is clear now. We are essentially trying to find elements and create a smaller subset array which maintains the order and gives us the desired sum. And there can be as many of them, not just one. So I'm going to start writing the code here with you. So for that, let's assume you're given an array like we saw in the previous slide, 2, 4, 6 and 10. And I'm going to start with a recursive approach. Again, I want to quickly emphasize one thing. In this problem, it's just asking you for a true or false if a subset is present. But you can think of this problem as a number of ways problem. Meaning, if I give you an array, you find all potential candidates that can satisfy your condition. So it's a number of ways problem. And as seen in the previous video, like the climbing stairs problem, and also the previous problem that we solved, which was decode ways. If you haven't already, I really encourage you to check these out. Both of these are also number of ways problem, and our method to solve the problem remains the same. We'll tackle that with recursion and then optimize it with dynamic programming. Why do we optimize it later? Just to do a quick preview, recursion would give us an exponential runtime algorithm. For example, 2 power n. We can optimize it with dynamic programming and create a polynomial time algorithm by storing repeated work and make it something like O of n. Again, this is just an example. I really encourage you to check out the previous two videos, both the climbing stairs and decode ways, which will give you the fundamentals you need to solve this problem. All right, let's jump to the code now. So the first thing I'm gonna do here is break this problem down and write code. And the way I'm going to do that is we'll define a function and we'll call it recursive subset sum, and the input to this function would be the array which is given to us, the total which is the sum in this case, which is 6, and an index you start with. And the first thing I'm going to do is base case. Always remember, when you're writing a recursive algorithm, base case is the first thing you do. This allows you to terminate the recursive calls, else you can this can lead to infinite recursion stacks, which will never end the program. If your total is 0, so what we are going to do is essentially subtract the total whenever we pick a number, and if the total is 0, it means you have hit one way of creating the subset, so you return 1. Else, I'm gonna write the Pythonic, use the Pythonic syntax here. Else if total less than 0, you return 0. And another condition, else if I less than 0. So what I'm trying to do is I'll start at this index. I'll try to see if I can include 10. So if you subtract 10 from 6, you get -4, which will hit this condition, and you will just return 0. So 10 is not gonna be a way in which you can pick this, and you'll move to the next index as a matter of fact. So and there could be a case where you go all the way and you're off the cliff of the array, which is I is less than 0. You still want to return 0 because there's no way. So these two are the off the cliff cases. The total can become less than 0, or your I can go out of bounds. All right. And if there's also a case where, as I said, the total is actually less than the current array element. So in this case 10, you simply ignore 10 in that case and you go to the next one, right? So I'm spelling that case out here, and for that I'm going to return, I'm going to call it recursive subset sum, again in short form, total and I minus 1. So as you see, I just take my total and I pass it to the next index. I do not subtract anything from it. The other case is, if all of these conditions are not true, I'm gonna return the recursive, I'll call the recursive function, but I'll explore both the possibilities, with and without my current element. So what I mean is I subtract my current element from the total. So in this case, I select 6 and decrement the index. So I move the index to the next one after selecting 6, or I ignore 6 and I still move the index. So I do not look at the subset. I start my subset at the very next index with 4. What that will do for us is it will allow us to create this subset 2, 4. And this call will allow us to pick this 6, and this call is going to allow us to pick 2 and 4. I want to quickly, take a moment and draw the recursive stack. I might not be able to draw all of it, but just to give you an idea, the way it will look like is you'll call this function at length -1, which is the last index. So you'll have two cases with and without. In the first case, you will essentially ignore because you'll hit this condition where total is 6, your element is 10. You'll simply move to 6. So you're at 2, 4, 6, and your total is still 6. And in this case, you're gonna come here because none of these conditions are gonna get satisfied. So you'll jump directly here and you'll explore 6 as an option, so your total will become 0 and you'll be at 2 comma 4. But as soon as you hit your total to be 0, you hit this case, so you're gonna return 1. And the other case will be you don't, which is this case, you don't change the value at all. So 6 total remains 6 and you're at 2 comma 4. So you jumped from here to here without changing the total. So you ignored the element 6. What this will do is it will also return 1 and it will give you another way, and we sum both the ways. So this call stack will return 2, and essentially you'll have two ways in which you can do this. So two subsets that are possible. I'm also gonna, let's first analyze the time complexity of this. And as discussed in the previous video, the way we calculate time complexity for recursive algorithms is O of branches to depth. And you can see the maximum depth would be you're going through all the indexes from right to left. So O of 2 power n. This is an exponential time algorithm. The question is, can we do better? Can we do better? And I'm again going to refer you to both the climbing stairs problem and the decode ways. The way you convert an exponential time algorithm to linear time is dynamic programming. And the way I'm going to do that is what you essentially do is create a space called, let me change the color, memo, which is a dictionary. And what memo is going to do is we create a key as soon as we enter this space, and the key will have a string. It will be a string key because they are hashable types. You'll concatenate the total with the changing variable, so the state. Now what I mean by state is whenever you call a recursive function, there are two things that are changing in this code. One is the total, so if you subtract, you change the total, and also the index as you make progress through different elements in the array. So this is your state. And what you do is you create a key where you hash the state, and you simply if you have this solution in your memoized code, you return you return right there. You don't execute any of this program. And if that's not the case, you save your solution. The way you're going to do that is let me find a space here. The way you're going to do that is the else and return is still going to be here, but you're going to save the result in something called temp, make the recursive calls, and you're going to say memo of key equals temp. So what you're essentially doing is every time you solve a subproblem, like you solve 2 and 4, you save the solution in the memo dictionary. So if you were to hit the same state in this branch, you can reuse what you've seen already and not solve for this again. And the time complexity in that case becomes O of total times n, where total can be a constant, so it becomes O of n. So what this means is you wrote a recursive program. I'm going to create some space and just re-emphasize the logic of the program. So you wrote a recursive program which had an exponential runtime. You use dynamic programming to convert it into a polynomial program of total times n. I'm going to simplify this and say O of n as an upper bound. Right? The way you did that is you added a memoization capability in your program where you stored solutions to subproblems. Awesome. I hope the idea was clear. Thank you for watching Cracking the Fang interviews. I hope you liked the video.